Hi there, can somebody allow me to share my screen?
Andre, I'm not sure if I have that power.
Thank you, I think it's fine.
Okay.
Okay, and you see my screen, right?
Yes.
Okay, great. So thanks to the organizers for preparing this conference, and thanks for letting me speak. So I wanted to tell you today about gravitational dynamics of quantum Hall states. Just let me put my laser pointer. Can you see my laser pointer?
You can see
I can see your pointer. Yeah.
All right, yes. So I want to talk about collective dynamics in quantum Hall states in real materials, as well as how to see it in quantum computers. So the basic idea is, of course, to study this collective excitation that you all know very well, the graviton mode. So in condensed matter system, of course, one of their main features is the existence of these collective modes, which are some kind of coherent oscillations of the medium, right? And we know that from the physics of liquid helium and also from ferromagnetic materials, where we have these collective modes that are generated by some local operator acting on the ground state of the system. And this induces some kind of coherent displacement of the entire medium. So we know very well that we have very similar physics in quantum Hall systems. For example, in the Laughlin 1/3 state, the spectrum of which is shown here, we have this magnetoroton collective mode, which is the density wave, right? And of course, this also includes spin here. So we also have the analog of the spin wave. So this is the quadratic spin wave dispersion that we also have. And here I assume 0 Zeeman splitting. So originally I wanted to talk about both of these modes, but since I don't have the time, I will just focus on the first one. And there have been some interesting recent experiments how to study the spin mode in this work by Andrea Young's group. And I can comment on these experiments in the discussion time if anybody's interested. So, but what I want to tell you about today is in two parts. The first part is this geometric quench, which allows us to study this graviton mode in the log wavelength limit. And this is something that we started doing a few years back with Zhao Liu and Andrei Gromov, and more recently also with Ajit Balram. And then in the second part, I will talk about some published work about moving from these material systems into the existing quantum computers, and where we might be able to see some signatures of similar types of physics. So motivation is to study this graviton dynamics, right? So the collective mode, which is present in all fractional quantum Hall states, is this magnetoroton mode. And here, this is for the Laughlin 1/3 state. And we know quite a lot about this mode. It has this nice single mode approximation description, which goes back quite a long time. There are also some experimental studies of this mode, which focus on the finite wave vector physics of this mode. But what's interesting, what was interesting for us mainly, is the long wavelength limit. So this part of the mode, which, as you see, is buried in the continuum of the energy spectrum. And the interesting part of that long wavelength limit of the magnetoroton is that it has this quadrupolar structure. So it's kind of like an emergent spin 2 degree of freedom, or more precisely, it has angular momentum 2 in this case. And it's described by this emergent metric, the geometrical degree of freedom. And these are some of the reasons why it was called graviton in this context. So what we're interested in is to understand how we can excite this graviton mode, and whether we can see something interesting in the dynamics that follows that initial excitement of this mode. And this is not completely obvious if you think about it, because as you see, the mode is buried in the continuum of the energy spectrum. So it might be kind of non-trivial to actually see something, even if you try to excite this mode. And so the tool that we decided to use to study this problem is the tool of quantum quench, which is, well, it's been quite fruitful, as you see on this slide, in recent years, because it allows for a very simple conceptual probe of new physics, essentially. And here are three examples of systems where this was useful. For example, in integrable 1D systems, there was this quantum Newton's cradle experiments. Then also it was important in strongly disordered interacting systems, where you can see signatures of many-body localization if you look at how the entanglement spreads through such systems when you quench them. And there you see this slow log growth of entanglement entropy, which is one of the signatures of many-body localization. And then finally, even more recently, in these experiments on Rydberg atoms, these quenches were also interesting because they led to this discovery of quantum many-body scars. Again, some interesting dynamical response of such systems when you do a quench. And you can see that the characteristics of that is some kind of coherent oscillations, which was puzzling because these systems are non-integrable. Okay, so we want to do some kind of quench for studying this collective excitations of quantum Hall systems. And we want to study this collective mode. So the key aspect of that collective mode is that it's connected with this quantum geometry in these systems. So of course we know very well that the basic physics of fractional quantum Hall states is this flux attachment, right? So if we have electrons, they surround themselves with these correlation holes, so they attach fluxes, and then that allows them to create this incompressible quantum fluid. And then the geometry arises when you think about deforming this fluid. So the key physics is invariant under sufficiently weak area preserving deformations of that fluid. And there has been a lot of recent work, devoted to understanding, the consequences of all this. And so formally, the way we describe this geometry is by this 2x2 metric, which describes essentially the shape of this flux attachment in these quantum Hall fluids. And so what will be important for us is that it's a unimodular metric because we preserve the total area of the quantum Hall fluid. And so we can parameterize it by these two physical parameters, which are Q and phi here. So Q is the overall stretch of these droplets, and phi is like a rotation angle. So if we want to excite this collective mode and the graviton excitation, the main point is that quench must be associated with the change in this metric, okay? So the idea that we followed is actually quite simple, and we called it geometric quench. So it goes back to, I guess, the first idea along these lines was given in Kunyan's paper a few years back, and then there are also more recent follow-up works by them. But the way we implemented this is just you take a quantum Hall fluid, which is normally in a perpendicular magnetic field, and then you just suddenly slightly tilt that magnetic field away from the normal direction, okay? So if you do that fast, you will throw the system into a non-equilibrium state, and there will be some dynamics happening. And the question is, what's going to happen with this metric that describes the quantum Hall fluid as a function of time, okay? So that's the basic idea. And here is more formally how we do it in practice. So we're going to assume that we start from like a fully isotropic system. So this metric, for example, the metric of the mass tensor in this system is purely isotropic. So it's an identity matrix. And then we suddenly stretch it along one direction, okay? So it's just stretched along X and elongated along Y. So this is, to the leading order, exactly what happens when you tilt the magnetic field. Or if you can change the mass anisotropy directly, you can also engineer it in that way. Then we assume that our system is closed. This is for simplicity, simulation reasons. So it means that it's going to evolve according to the Schrödinger equation with this new Hamiltonian, which depends on this new metric, which is not isotropic anymore. Okay, and now the goal is we want to find the equation of motion for these Q and phi parameters, which give us the metric of the fluid in a time-dependent state. So how do we do this? So we did it by brute force at first, which is basically you take your exact time-evolved state at some time, and then you look for the maximum overlap with an entire family of Laughlin states for all kinds of metrics G. Okay, so we can generate a family of Laughlin states with arbitrary metric G, and then we, essentially variationally go through all the members of that family, and we find the one that has the best overlap with our time-evolved state. So if this maximum overlap is sufficiently close to 1, then we can be sure that we found the right description of that state at time t. Okay, so of course there are some assumptions that go into this. One assumption, obvious one, is that our quench is sufficiently weak so that there is still some kind of Laughlin type description of the system even after the quench, right? If this is not true, then we have to find another way to find this metric. Okay. So first we looked at these kinds of quenches, and so here are some results. What you get from doing that. This is the dynamics for these metric parameters Q and phi as a function of time. And this is done for the Laughlin state of bosons with contact interaction, where we change the anisotropy essentially by 30%. So this parameter A, which is essentially the mass anisotropy, is changed from 0 to something like 0.3. Okay, so what we see here is that the dynamics is actually quite simple, quite nice. There's a coherent type of dynamics, at least for short to moderate times. And we can essentially fit this dynamics by very simple harmonic type equations. So if we look at the dynamics of Q, the stretch parameter of the metric, it's essentially a sinusoidal function, whereas the phi parameter, the rotation angle, is basically piecewise linear function. Okay, so the parameters that go into this, and this we can see just from eyeballing these plots, right? So the fitting parameters that go into this is some energy scale that we call E gamma. And from the fits, we see that energy scale is something like 1.3 in this case. And there is this overall prefactor for Q, which is the essentially this post-quench anisotropy. It's very close to that value. So what's the physical picture here? What happened during this quench is that we basically excited this graviton degree of freedom, because that's precisely the one that sits at this frequency 1.3. And how do we know that? Well, we also looked at some more quantitative parameters to give some support to this interpretation. We looked at this spectral function, which is essentially the matrix element between the ground state of your system and all the excited state in your system, and the operator that goes into that spectral function is an appropriate quadrupolar pseudopotential, which is the one that captures the effect of mass anisotropy. And that quadrupolar potential, that spectral function defined for that operator, is extremely sharp, as you see here, and it has this peak precisely at the same energy 1.3. So even though we quench the system, the quench was designed in a rather special way so that we don't get some garbage, from a continuum of frequencies, but we have a very sharp, essentially single frequency, which contributes to this dynamics. Then the other thing that we did for this, we also used Andre's biometric theory, and we essentially derived the effective equations of motion for these parameters q and phi from that biometric theory. And as you see here, these equations of motion are they look quite scary. They are obviously quite nonlinear equations. But when you linearize them, you get these much simpler equations, which exactly give you the solution that we had on the previous slide. So this is exactly the solution for these linearized equations that we have here. And the important thing is that by linearizing these equations, you essentially don't lose any information on these timescales that we had in this plot. Okay, so why can you do that is something that we still don't fully understand. It seems like it should be a highly nonlinear problem, but at least for this type of quench, it has a very nice, also linear kind of interpretation. And another nice thing from all this is that we can essentially use this geometric quench and the microscopic calculations that we developed for that to kind of gauge the, the appropriateness of this effective biometric description. So we can really test how well it describes the microscopic dynamics, and we can maybe push it to some regimes where it may not be so well defined, and then maybe we can learn how to extend it in various ways. Okay, and so just to advertise something that we recently did on this. So we also looked at what happens in bilayer systems, because bilayer systems, of course, are much more complicated. They have multiple collective modes. So as you see here in this bilayer system of bosons at 2/3, we have two modes. One which is again this quadruple mode, similar to a single layer system. But then there's also this dipole mode, which is kind of like a photon mode. It's just generated by, in the single mode approximation, it's generated by the difference of the density operators in two layers. So that gives you a spin 1 degree of freedom. And that mode is actually seems to be even lower in energy than the quadruple mode in many cases. So it turns out that we can probe these modes either individually or we can couple them. So one way to probe the spin 1 mode is simply to apply electric field in one of the layers. And what this will do is it will just induce a relative displacement of the electrons in two layers. And we've seen that this gives, again, a very nice coherent dynamics for this spin 1 mode. And the graviton mode, the quadruple mode, can be similarly probed if we do mass anisotropy quench. But now it's much more complicated because this mass anisotropy quench is not only going to excite this quadruple mode, but it will also excite the combination of two dipoles, and it will also excite the quadruple mode from a single layer system, which was quite surprising to us because that mode in a single layer should be at much higher energies, but still it appears quite nicely in the dynamics, which was quite interesting to us. Okay, so that's something new that we did along those lines. Now, because I don't have too much time, I want to tell you how we can also see some signatures of this in systems that we can study on quantum computers. And so the basic idea for this is it's going to be well known to you. So the idea is to take this quantum Hall system and stretch it into a thin cylinder, okay? So the reason why we do this is because in this quasi one-dimensional limit, when the cylinder is very thin, we can significantly simplify the problem because the long-range hopping processes due to Coulomb interaction become energetically prohibited. So we are only left with essentially this center of mass hopping, preserving hopping of electrons from two neighboring orbitals to their next neighbors like this. But if you try to scatter across longer distances, then that's prohibited energetically, okay? So in this limit, the Coulomb Hamiltonian is very simple. It's just three types of density-density interaction terms, classical terms, and then there is this hopping process, which I just described. And that limit is nice because it's a frustration-free limit. The Hamiltonian is frustration-free, and there's an exact ground state, which you can write for any values of these parameters, which depend on the circumference of your cylinder. And so the exact form from the ground state is this. So there's some kind of operator, which is the squeezing operator, acting on the root state, which is this 100, state. So this stuff has been known, as you see, for some number of years now. So the new thing here is what we're going to do with this is we're going to turn it into a spin chain model. And then we're going to show that if you put anisotropy into this Hamiltonian, you can still see some signatures of this graviton dynamics that we had in the 2D system. And this is something that I think hasn't really been noticed before. So the mapping to the spin chain goes as follows. So basically what turns out is that this Quang-Hall model in the thin torus limit maps to a particular spin model, which is called the PXP model. And this model has recently been studied a lot because it describes the Rydberg atoms in this strong Rydberg blockade regime. So the way the mapping works, so first the Hilbert space, if you basically start from your Laughlin root state, and then the Hilbert space contains all configurations that are generated from that root state by squeezing any two electrons, so just the nearest neighbors, okay? So you generate all the configurations with only nearest neighbor squeezing, and the number of those configurations grows as a Fibonacci number as a function of the number of electrons. So in the context of spin language, it means that it's like a spin half chain with the constraint that you can't have two neighboring spins both being excited, okay? So you start from all spins being in the ground state, and then you allow all configurations which do not have pairs of spins who are nearest neighbors that are both excited. So you exclude all the nearest neighbor excitations, and that gives you the same Hilbert space. Now, the way you map the Hamiltonian, you can work out with a little bit of effort, is these density-density terms, they just become diagonal terms. So they're diagonal in the Z basis for spins. And the hopping term becomes this PXP model, where X is the usual Pauli matrix and P is the projector on the ground state of the spin. So it has this form in the usual representation. So the meaning of this PXP Hamiltonian is that it allows you to flip a spin if and only if both neighbors are in the ground state. Otherwise, you can't flip. Okay, so that's formal mapping. Now, this is useful because you can work with a much simpler spin problem, and that's something you can put on a quantum computer. So the first thing we did was just to check that some of the physics survives in this kind of system. And indeed, if we do an anisotropy quench in this thin torus limit, we find exactly the same type of biometric oscillations that we've seen before, the same type of dependence of Q and phi. And again, we can look at the spectral function to confirm that indeed there's a quadruple degree of freedom with spin 2. That's the dominant contribution to this dynamics. And the energy of that degree of freedom is precisely sets the frequency of these oscillations. So that's nice because we preserved some of the physics in a much simpler model. And that's something that we can hope to put on a quantum computer. The problem with just going ahead and putting this on a quantum computer is that, once you start doing this, you realize how hard it is to actually get useful results for, quantum many-body dynamics on these quantum computers that we have available at the moment. And the reason for that is if you naively try to trotterize your Hamiltonian to implement the evolution operator, you realize that you require a lot of entangling gates to do that. And these gates, they are quite, well, they leave much to be desired at this point in technological development. So you can't implement this type of dynamics just by simple trotterization of this Hamiltonian on a quantum computer. So the way around these issues is to use these ideas of quantum classical variational eigensolvers. And that idea is basically, if you want to get your time-evolved state at some time, you use some kind of variational ansatz to approximate that state. And that variational ansatz depends on some simple quantum gates and some classical parameters, which here are some angles theta and phi. And these variational angles are something that you variationally optimize on your classical computer. So you do a variational optimization on a classical computer, you get these angles, and then you go back to your actual quantum computer and you get your time-evolved state in that way. So the particular ansatz that we use in this case is a combination of these gates, which are essentially like simple Z rotations, and then this control Rx gate. And the reason why we use these gates is quite interesting, but I don't have the time to really talk about it. It's connected with this recent works that study quantum many-body dynamics using this approach based on time-dependent variational principle, which you implement in manifolds of matrix product states. So this has been used to study, for example, these Rydberg atom chains, and it was quite, it gave some nice results there. And we can borrow some of these ideas also in our context here. So that's how we actually implement the dynamics on a quantum computer. And in the last couple of minutes, let me just show you some results that we got out of this. So this is the basic results that we can get at this point. So we do a quench in this spin chain model. We do mass anisotropy quench or tilting the magnetic field. And in the spin chain model, it basically amounts to doing like a Bogoliubov rotation on this X operator dependent on this anisotropy parameter. Okay, so that's what happens with quench in this language. So when we do this on a quantum computer, so these are examples for 5 qubits on IBM. So that's about 15 flux quanta. We calculate here 3 things. This is time evolution of some local density at a certain magnetic orbital. This is some local correlation function, and that's something that's kind of like a fidelity, but not really the fidelity. It's overlap of your time-evolved state on this classical product state, which is like a vacuum state in this case. So as you see, all these 3 quantities, they have exactly the same frequency and they evolve precisely as we expect them from the, well, we can't directly test here the biometric equations because, you know, we're not measuring the metric directly because we don't have a nice simple operator that we can measure to do that. So that's why we looked at things like local observables and local correlation functions and something like this fidelity. So we can see that, you know, probably there's a similar type of physics going on, but I guess we're going to think a little bit more whether we can also directly measure the metric. in this case. So the two kind of things you can see here. So the ED data is this blue line, and then the actual results from one of the IBM quantum computers is this orange one. Okay. So you can see that in all cases we have reasonably good agreement, but due to hardware deficiencies, the agreement is obviously not perfect. And moreover, if we try to go to bigger systems at this point, the agreement still deteriorates further. So we need to think a little bit more whether we can still optimize the answers that we use, and perhaps the other thing we're going to try is also to use a different quantum computer. For example, there's the trapped ion quantum computers, which have slightly better gates. So perhaps we can see this time evolution in slightly bigger systems if we use those platforms. Okay, and time for me to conclude. So here are my conclusions. So I talked about this geometric quench, which is a certain tool that we introduced to basically study collective dynamics in fractional quantum Hall states. In simple Laughlin states, it allowed us to basically check the prediction from this biometric theory, which worked reasonably well. And then I also tried to convince you that we can see some signatures of this also in the simplified 1D model, which is actually very nice because it's implementable on quantum computers that we already have available at this point. And there are lots of open questions, and I want to advertise just a few of those. One important question is this higher spin modes. So the particular quench that we did here is the one that probes this quadrupolar excitation in the spectrum, what we call the fractional quantum called graviton. And that's the one that responded predominantly to the quench that we did. But we also see that there are, if you wish, higher spin cousins of this mode. For example, if we go to slightly higher energies, then we can design the spectral function that probes this octupolar excitation. And we clearly see that in the spectral function, but we need to find some more physical ways to actually excite such modes. And that's something interesting because these modes are not really included in the simplest form of biometric theory, which we had on the previous slide. Then, of course, another interesting question is how do you excite non-abelian modes? For example, the neutral fermion in the 5-half state, which has the spin 3-half. So because, it's a 3-half spin, it becomes a bit less obvious how you're gonna be able to excite it. So probably because it's a neutral fermion, you need to change also the particle number in this case. So maybe if you have like a nearby quantum dot and you tunnel an electron locally or something like this, maybe you can excite such a mode. And then another thing which is quite interesting in what happens with nematic quantum Hall states, because in those cases we have this gravitational mode which actually becomes gapless. So it might look something like this. And now because it's gapless, it's not quite clear what's the best way to probe that, because maybe there's like a multitude of frequencies in this case. We're not quite sure how to measure the metric in that case because we don't have a variational wave function, which works well for that case. But it's certainly something that's very interesting to think about for future work. And with that, thank you all for your attention.
Thank you, Zlatko. Yeah, if anyone has any questions for Zlatko